This integral looks horrible. It did spend me some hours to come up the answer, and I wanted to share with you. Now, the first step, I okay. Let me verbally express. I'm I write sine square theta, sine squared x, sine squared x. Then this two could be written in the front, right? So therefore, this becomes a half. Well, anyhow, I write down this is equal to 0 to and half log sine square x. Well, because this two cancel with that two is equal to sine theta. Similarly, I write half log cosine square theta x. So, right, this two cancel with that two. Okay, this one is equal to what? This one is equal to sine x cosine x and the dx. Good. And then half times half is 1/4. Integral from 0 to half y. And here, well, this is a natural log sine square x. This is a natural log 1 minus sine square x, isn't it? This one is equal to the derivative of sine square, right? This derivative with respect to x would be 2 sine theta times the chain rule times the derivative of sine, which is a cosine. So this one is equal to that. Then it's obvious that we can replace sine theta by something. Say, well, I prefer write x instead of let sine theta be sine square theta be x. So that will be 0 is a 0, half pair becomes a 1. So it becomes a log x and a natural log 1 minus x, right? And dx. Yeah. I substitute sine squared x as x because these are just dummy variable. I can write any notation. So I use x anyhow. So the integral is much easier, compared to the given one. Now then we start from here. We have some wonderful treatment. This is the integral from 0 to 1 and log x. Now we expand this one, log 1 minus x, as a Maclaurin series. See, that is a sigma n negative x to the n from 1 to infinity. Yeah, and then dx. Well, if you don't remember that expansion for Maclaurin's, we can use this, right? We know this is equal to x plus x squared plus x cubed plus x fourth, right? That is obvious. You divide this one by that, divide 1 by 1 minus x, you get that. Then we differentiate both sides, not differentiate, integrate. Integrate both sides with respect to x. So this will be negative log 1 minus x. Yeah, this side will be 2x. I forget 1, huh? Sorry, 1 plus. Let me try. This is 1 minus x. The first one is a 1. 1 minus x plus x. Yeah. Next one is a plus x. Okay, I'm missing 1 in the first term. Sorry. Yeah, so the first term integral is x. The second one is half x squared. Then 3x cubed, and so on. So that will be equal to sigma xn over n. Yeah. Since this is negative, see? This is negative. So positive log 1 equal to negative that. Okay? See, that's it. That is, see, that is my own experience of memorizing this expansion as this. Yeah, then, okay. Then what? Then this one is equal to 1/4. Now I'll put a negative outside. Integral from 0 to 1. And I leave 1 outside and 1 and sigma 1 to the infinitive xn, right? And there's log n. I'm sorry, I forget log n. Yeah. Now, then what? Then this is equal to negative 1 over 4. I can I put a switch this operator, this sigma first, and 1 over n, then integral from 0 to 1 log x. Xn dx, I can write the d xn plus 1, right? N plus 1. Yeah, that's correct. Then I can work carefully because very easy to come up error. Now this 1 of n can be put outside, right? 1 n plus 1 integral log x dxn plus 1. Then I can use by parts, udv, right? So this is equal to 1/4 sigma 1 to infinity. This is by parts, uv, right? U times log x from 0 to 1 minus integral from 0 to 1. This 1 times this derivative. This derivative is 1 of x, so it becomes x to the n. Okay? Right? This 1 time this derivative becomes this. Yeah, and continue from here. And this is obvious that when x equal to 1 is 0, when x approaches to 0, we can use L'Hopital's rule. Now, okay, let me skip L'Hopital's rule. This is equal to 1, or this is equal to 0. Huh? So my integral becomes negative 1/4 sigma 1 to infinity n plus 1. This integral is equal to 1. Negative 1, this is negative. This is equal to xn plus 1 over n plus 1. Right? So this negative cancel with the negative becomes a positive. Sigma 1 to infinity. This will be n minus 1 square. This is 1, right? This is 0, so equal to 1. Wow. Very good. Then what? Then here, I'm using partial fractions. Sigma from 1 to infinity. This is equal to n, A, right? Plus n plus 1b plus n plus 1 square c. Partial fractions. Let me skip the determination of ABC. I think you know how to find ABC. Here A is positive 1, B and C are negative 1. So this one equal to 1/4 sigma 1 over n minus 1 over n plus 1 minus 1 over n plus 1 square. Okay. Excuse me for the skipping this, but it's just how the break work. Now then this one is equal to 1/4 sigma 1 over n minus 1 over n minus plus 1. That is for these two terms, right? Minus 1/4 for that one. N plus 1 square. Yeah, that's correct. Yeah. This is a telescoping series, right? This is telescoping series, and it's equal to 1. So that is this. This is equal to 1. Huh? Minus 1/4 yeah. This is equal to what? This is equal to this. This is equal to 2 square plus 3 square plus 4 square plus and so on, right? If we add 1, that will be a Basel problem, no? Right? We're missing 1. So in other words, this will be sigma 1 to this one, n square 1 minus 1. This one, start from, well, minus this one will be this. Well, I hope you understand me. And this is a Basel problem, okay? I think this is a 1/4 minus 1/4 over pi squared over 6 minus 1. So let's end up with half plus minus, minus 24 pi squared. Yeah, that is the very answer to our this incredible integral. Well, I hope everything is clear, and this is just wonderful integral. The answer is a good. I hope it's correct. Thank you.